All right, let us look at this third. Let's look at the third case of this projection. So of this projectile, when an object is projected at an angle of inclination with the horizontal. So we have the motion. Look at here. Now, since this object is undergoing a motion in two dimensions, motion under gravity in two dimensions, that is the projectile motion. Now, we want to look at when the object is projected at an angle theta with the horizontal. Now, this velocity, this is the velocity of projection. It will have the vertical and the horizontal components. So, resolving this to vector resolution, we are going to be having a triangle like this. If you decide to trace this down to this point and trace this down to this level and trace it to this horizontal. So at that point, we are going to have a rectangle. Then you bring out this. This will become the resultant, okay? This one becomes the resultant, tracing it from here down to this point. So it will become the resultant velocity, and a resultant force or a resultant vector can be resolved into what vertical and horizontal components. So that is what we have, what the component, the horizontal component of this velocity u is known as what ux equal to u cos theta. So if we do that now, according to SOHCAHTOA, we'll resolve it to like this, and that of y, which is this vertical component. And remember, projectile motion, two independent motions are happening at the same time. The one that is affected by force of gravity is the vertical motion. Now we are going to first of all consider as the object is moving along this parabolic path. Now it will continue to move with this velocity resolved in its component. When it gets to this maximum height here, at this maximum height, we only have the horizontal velocity here. Then the vertical velocity here becomes what? Zero. And also the final velocity of this object, which is v at this point, is also what? Zero. And then as it begins to come down, as it gets to this point, we will now have that of y component to become more negative. Then as it's coming down, finally as it lands here, we only have this horizontal velocity, which is this what? Ux. Ux is the only velocity that we have here at this point. And from here to this point here is what we call the range. This is the point of projection, and here is the landing point. So the distance between the point of projection to the landing point is known as what? The horizontal range. So the range is the horizontal distance. Why? From here, this point here, see this point down to this point here, is called the maximum height. So it's measured from the level of projection. So this is the level of projection here, okay, down to the height. So we are going to, first of all, consider the vertical motion now before we can get the value for this time. Now let us look at the parameters we are going to look at. Time to reach maximum height. Maximum height. We need to know this one. And also time of flight. Time of flight. Time of flight. Then we also know the maximum height itself. So let us look at how we get the formulas. Maximum height and also the range. This range, which is the horizontal distance. So let us look at how we can derive it from this. And remember, I told you that the horizontal component of u, which is ux, equal to u cos theta, and that of the vertical component of u is what? U sin theta. Now, looking at this vertical motion, let us consider the time to reach the maximum height. Remember, our equation of motion become, now we want to consider the vertical motion will become Vy, that's V subscript y equal to what? U of y. As we are going upward, now we are projecting against gravity, which to give us a minus gt. So remember, this is our equation 1 of motion. Now, at this point where we have, remember that U of y is equal to U sin theta, okay? U sin theta. So this U of y is what we use sin theta. We are going to use this one to replace this. And remember, getting to this point, this V of y is 0. V of y is equal to 0 because when you get to the maximum height, then the V becomes 0. So which means here is 0. We have 0 equal to what? U sine theta minus what? gt. So we can take this gt to this side, become positive, because 0 plus gt, we have gt equal to u sine theta. Now, we are looking for this time. T is equal to u sine theta all over what? G. So this is the time it takes to reach the maximum height. Now, what about the time of flight? The time it takes to reach the maximum height is the time it takes the projectile from this point here. This is what? The point of projection to get to this point. So that time is also equal to the same time to get down. So the time of flight now is not the time it takes to get to this point and also come down. So time of flight is equal to 2 times the time it takes to reach the maximum height. So time of flight is represented as capital letter T, which is equal to 2t. Time of flight is this. Then we can just say t is equal to what? 2. What is our small t? U sine theta times u sine theta all over what? G. So the time of flight is given as t equal to 2u sine theta all over G. So this is the formula for calculating the time of flight. Now let us look at the maximum height. Remember, this particular projection is where we are projecting at an angle with the horizontal. In my previous videos, I treated when an object is projected vertically upward, and also when the object is projected horizontally from a height above the ground. So it's not the same way we calculate the time of flight and the time it takes to reach the maximum height. Now let us look at the formula for the maximum height. So the maximum height is the vertical distance. Remember, it is what? Vertical distance. We are going to be using one of the equations of motion where we have v squared. So it's now become vy squared equal to then u squared, that is uy squared, minus 2g. Now this will now become our h, okay, since we are not dealing with distance, which was vertical distance. And remember, your final velocity is 0. So this will become for 0 equal to, what is our uy? Remember, the horizontal or the vertical component of the projected velocity is u sine theta, then all squared. Remember, this one is having square, minus 2gh. Now, let us take this one to this side. So this will now imply that 2gh is equal to, now distribute this square to both sides, become u square sine square theta. Then we are going to look for h. H is now equal to u square sine square theta all over 2g. So this is what we use in calculating the maximum height for a body projected at an angle. So take note of this. This is how we get this. Now let us look at the next one, which is the range. Now remember, the range here now, at this point, there is no component for the velocity anymore. We only have what? This what? Velocity. At that point, we will now have the range is equal to what? Ux multiplying the time of flight. That is the time, because the time it takes to get to this level and also comes down. This is the point of what? The final landing of the object. Now let us look at how we prove this formula. Okay, we say that what? The range is equal to, that is the horizontal component of the velocity multiplying the time, which is time of flight. And remember, the horizontal component of velocity is u cos theta, okay? So that is u cos theta. Now, and also your time of flight is equal to 2u sine theta all over g. Now, we are going to substitute these two values into this formula here. So we have range is equal to u cos theta multiplying 2u sine theta all over g. So now let's go. So this will now give us 2, okay, u cos theta or sine theta sine theta cos theta all over G. Okay? Now let us bring out this u outside. To bring that u, can have u times sine theta. Okay, that's 2 sine theta. 2 sine theta cos theta all over G. Oh, sorry, there is an omission here. We have u here. We have u here. U multiply u become u square, okay? So this will now give us u square. All right, sorry for that. So that's u square. Now remember, in our trigonometric identity, under compound angles, we are having sine 2 theta as equal to 2 sine theta cos theta. So we are going to use this identity now, this one, to replace what we have here, so that at the end of the day, we will now have our range equal to u square sine 2 theta all over G. So this one is the formula which we use in calculating the what? The range of this projectile. Now the last thing I want to show you, what if we are asked to find the rebound velocity or the velocity immediately after projection? Let's say 2 seconds after projection. So what do we do? So that one, we use different formula entirely. Now let's see. Okay, now let's assume we are asked to find the velocity, let's say 2 seconds after projection. What we are going to do, the velocity will give us v squared equal to the ux squared plus uy squared. Now, this will now imply to us that v is now equal to the root of ux squared plus uy squared. Now, the question now you are going to ask yourself, where do I get my us squared and uy squared? Now, it's very easy. Since we are considering a vertical motion, your ux squared, we have, which is this word, u cos theta. So that is for only for horizontal motion. So this u s squared is what? The horizontal motion. Okay? Then uy squared is always 0. But now, we are going to look at v squared equal to vx squared plus vy squared. Now, v is equal to what? The square root of vs squared plus vy squared. Now, since we are saying vx at this point, vx is equal to ux because the velocity remains constant. Vx equal to what? Ux at this point, the final landing point of the projectile. So now in that case, for us to get this horizontal component, to get this effective velocity, we will consider the vertical motion for Vy. Remember that what? As the object is going, we have, when you are going projecting upward, we have V equal to U plus, that's Uy plus AT. So this is now what? Vy. And this AT becomes G as usual. Now, this time is a time that will be given to us for what? The projection. Let's say immediately, let's say 2 seconds, immediately the object is launched. So this time now is not the time to reach the maximum height, and it's not the time of flight. So in your calculation, you must take note of that. Then from here, we can get our Vy. So Uy is 0. So we can have Vy equal to what? Gt. So this is the velocity. And this is for your vertical component of this velocity. Then the horizontal component, like I said, the u of x and v of x equal to what? U of x, because it's constant. The horizontal velocity continues to remain constant as it lands. And for there, you can get u of x to be equal to what? U cos theta. So from there, this value, you plug it into this and you get your effective velocity. Or we can also call this what? The rebound velocity, or the velocity, let's say 2 seconds after projection. So you must find the resultant component of the two velocities. So you don't just calculate. So I hope this video helps someone. So in my next video, we are going to bring out calculations of different forms of this projection. If you find this class very interesting, please help us to share this video so that we can get to greater number of students on this platform. And they too will also learn and benefit from this video. As you do so, God bless you. Bye.